Remember the functions x to the n, 0, 1. So that's f1. Parabola, cubic, quartic, right? And the umpteenth version, x to the n out here. What did we find? That if you look at that interval, throw the point 1 out because 1 to the nth is 1. Every other fraction is strictly less than 1. So an arbitrarily high power is going to converge pointwise to 0. So the limit function is down here, right? It's the 0 function, and that's open there. Closed here, open there. So if you say, okay, there's a capital N, and once I get past that, it implies that x to the n minus the 0 function is less than some preassigned epsilon. I will say to you, well, that can't be true for every x here. It may be true for most of them, all the way over to here, but eventually you will be defeated. Right? I can slide a little bit over so that no matter what n you pick, it's going to be greater than or equal to epsilon. Because this thing, remember, it jumps in the last minute. And it's jumping, you know, if it's x to the millionth power, it's damn near 0 all the way along. Then it gets close to 1, and suddenly it goes straight up almost, right? Not really straight up, but very close to being straight up. What would its slope be? Not 999, or x to the million, a million x, right? Evaluated in 1 would be a million, right? The slope would be a million. So that's damn near straight up. So it rises so fast. Yes, sir?
Are you assuming that Fn converges to f of x pointwise? That's the
Well,
or do you not?
No, I don't think I have to assume that in advance because immediately what I can say here for a particular x, epsilon is fixed. This is a Cauchy sequence for a particular x. You know, take out the functional dependence. Put a particular x in here, and then I have a sequential term an. The difference in the two is arbitrarily less than an arbitrary epsilon, right? So what is that? That's a Cauchy sequence for every x. So every x is a Cauchy sequence. And what do we know about Cauchy sequences? They all converge. What do they converge to? A pointwise limit of this thing. So built into this statement here is the existence of f, the pointwise limit function. If this is happening, I'm supposing that it is, right? I'm supposing that this is happening. And the supposition is enough to force the existence of the limit function. You see that? For a particular x, it's just a plain old garden variety Cauchy sequence that converges. You would question them. You said, like, where the hell did the f come from? It's there, right? It is implied for a particular x, it's Cauchy at every x. That's the limit function. But now, what's the condition for uniform convergence of the fn's to f? Must find an n of epsilon, right? Such that n greater than n of epsilon implies fn of x minus f of x absolutely less than epsilon for all x in A. So that's the condition. Where's that come from? You'll laugh when we prove this. You know what you do? Standard way to prove this is to take this expression. Take the limit as m goes to infinity. What would that be? Okay, every one of these is less than epsilon, right? Pardon?
I just wanted to show you
I guess that's all we can have. Okay, I take the limit as n goes to infinity, so I get this term right here. How big can this be if these things are all less than epsilon? Does this thing have to be less than epsilon? Or does it just have to be less than or equal to epsilon? Certainly can be greater than epsilon, yeah? There's no way this can be greater than epsilon, because then it'd be one of these that was greater than, between epsilon and the value of this thing, right? So the most that this can ever be is epsilon. It's like the soup, if all the numbers are below 2, then the supremum of that set of numbers doesn't have to be below 2, does it? But it's never above 2. Right?
How do you know when it's less than or equal to, or just less than epsilon?
Okay, that's what we're saying. First of all, here's the good news. Being less than epsilon or less than or equal to epsilon are interchangeable in the definitions for continuity and convergence. It's traditional to use the strictly less than, although I've seen books, Walter Rudin, in his classical book on analysis that we ought to use here, uses less than or equal for some reason. Other books just use less than. In training,
just take a less than.
right. But this came for a reason. Just didn't say that. Let's go through this again. Suppose I have a collection of numbers, and all of those numbers are strictly, or equal, strictly less than 2. How big could the supremum of those numbers be? Supremum of that set. They're bounded above by 2. The supremum could be 2, couldn't it? Even though all the numbers are strictly less than 2, the supremum could be 2. So you have to provide, if you're taking a supremum, we have to do it more equal. That's what I'm doing over here. As I let n go to infinity, what I note is every one of these things with an n and an m is less than epsilon. And basically, when I let n go to infinity, I'm finding the supremum of these. What's the supremum of these? They're all less than epsilon. So the supremum is never greater than epsilon. It's less than or equal to epsilon. So this limit has to be less than or equal to epsilon. That's it. And you with me on that, Matt? Does it make sense? Huh? Okay. These things themselves are always less than epsilon. So the supremum of all these things is less than or equal to epsilon. So when I take the limit here, I'm still less than or equal to epsilon. Okay. All right. So we have this now. But, and this is the cheater. This is really cheap. This is done all the time. Less than or equal to epsilon equals that's less than 2 epsilon. Or less than 2 epsilon equal epsilon 1. There. That's kind of, that always seems rather specious to me, but what I can do is go back and let epsilon prime be twice the epsilon I'm using. And when I get to the end here, and I have the less than or equal epsilon, well, that's strictly less than epsilon prime. Okay? So it's like I go back, it's a redo. Now I go back and I pick epsilon equal to some epsilon prime over 2, which I fixed at the outset. And then I conclude at the end that the difference between fn of x and f of x is less than epsilon prime. But that's uniform convergence. Okay? So the way you prove the way you prove the Cauchy criteria for uniform convergence is to assume the usual thing for Cauchy. The nth term and the nth term, the absolute difference is less than epsilon. And show that by taking the limit of one of these sequences, I get the uniform convergence condition. It's kind of a cheap proof, but it's useful. It's useful because we can use this to prove the Weierstrass test.